Alright, today we're going to talk about 16.6 parametric surfaces and their areas. So this is this is the start of the second half of the chapter. This is kind of where everything starts to roll into one, where it starts to actually have meaning for everything that we've done in the first half of the chapter. This particular unit is quite lengthy as far as the amount of time it's going to take. This is going to take several videos, and my goal here is to keep each one of these videos to under 15 minutes. It's just actually easier for me to upload that way. So it might be in the neighborhood of 6 videos or so by the time we're done with this thing. They may not all be 15 minutes, but I want to try and keep them down to that if possible. Alright, so what we're going to talk about first is this first page is really just kind of an overview. It's an overview of what we've done from 16.1 to 16.4, and then we're going to talk about how we're going to use that stuff 16.6 to 16.9. Notice 16.5 is not in there. That's the last section that we did, and that was just talking about the curl and divergence, which we're going to use in the rest of these, but that wasn't anything specific to a concept. It was just how to do something for the most part. Okay, so in 16.1 to 16.4, what we were talking about was we had some kind of a curve, and we defined it as C. And that curve was some kind of a one-dimensional curve, a 1D curve. So it might have been, you know, something that looks like this. Who knows what it was, but it was some kind of a one-dimensional curve. And yes, we could have had this curve defined in even three-dimensional space. Then you might have even asked yourself, well, wait a minute, that curve there. That curve there is the first one's actually two-dimensional. Now the curve itself is not two-dimensional. The curve itself only has length. It doesn't have a thickness to it. It doesn't have a width to it. It's just a length to it. So it's actually a one-dimensional curve. The curve also could have occurred maybe someplace down here, you know, someplace in the XY plane, but in a three-dimensional space. Or technically the curve could have even been floating around, and I will give this some depth here in a second so you can see. The curve could have been floating around up here, you know, all this stuff in 3 dimensions. But again, the curve itself is excuse me, has no thickness, has no width to it. It's just a one-dimensional curve. It only has a length to it. And we could have defined it like we did in the first one right here, or we could have defined it in the second one, excuse me, as some kind of function of x and y. Okay, and this is, if we use this as a function of x and y, it's what's called a scalar function. Oops, completely misspelled scalar there. Scalar function. Okay, and it's called a scalar function because when you input things for x and y into your f function, you got out a z value. And this is kind of what we did when we were talking about how to define a line integral over C. And what we had done was maybe that there was some kind of a z value associated with every point on this graph. So when I've got a point here, there was a z value that might have been right there. When I just talk about this point right here, there was an output of a z value right here. There was an output of a z value right here, output of a z value. So for every value on this thing, there was an output of a z value. And then what it did was kind of create this ribbon idea. And then what we could do is we could find the area of that ribbon that was created over top of our curve. And if this bottom piece here, this piece right here was our c value, then what we could do is we could take the integral over c of f of x, y, or of all of our z values with respect to the length of the arc that this thing created. And that was what's called a scalar function, because again, you input x and y, you got out a scalar, you got out a number, you got some kind of a value for z. But then we also had the possibility of this third type, which was a curve which was floating in space, so it was not just defined in the xy plane. And when you have something like that, what we actually had was a vector valued function, because you could create vectors all along this thing, and those vectors create the actual arc of this thing floating in space. So a vector leads to every single one of these things. So this one here would be a vector valued function. And when it's a vector valued function, we actually define that to be capital F of x, y, z, where capital F represents your vector, and what you would do is you would input some x, y, and z values, and what you would get out of that is a vector, which is why we call this a vector valued function. And the idea here was if there was some kind of a vector field that this thing was running through, so let's just go with yellow. So maybe there's vectors, a vector field pointing this direction, and then this way, and then this way, and then this way, all those different directions. The idea was if I were to start here and travel this direction along my path, does the yellow vector field help or hurt me? So what we're actually defining there is the amount of work done in order to get from one point on the curve C to another point on the curve C. So what we have was we would take the integral over C of f, our vector valued function, dotted with dr, or the change of change of the r, change of the vector vector valued function, and we would get the work done. Again, so it's how much work is done along the curve by the vector field. How much work is done by the vector field along C. So again, the idea was how did it help? How did it hurt? Or maybe it did neither. And that was the general concept from that. In all these cases, again, one of the main things to remember here, in all cases, C is a one-dimensional curve. Again, very important concept. And that was kind of the crux of what we did from 16.1 to 16.4. All right, but for the second part, for the 16.6 to 16.9 part, now instead of doing this over a curve, we're actually going to do this over a surface, S. And so the idea is, let's just draw a really simple surface here. Let's draw something like a cylinder. This is a three-dimensional surface. Actually, I apologize, it's actually a two-dimensional surface, but it's in three-dimensional space. So what we've got is, we've got our cylinder, and the idea is we're talking about just the surface of the cylinder. So we are talking about the bottom part of the cylinder. So you're going to have a surface here associated with this. And then you're going to be talking about the top part of the cylinder. Let's see if I can draw this. It's going to be close enough. And you're going to have a surface associated with this. And then what you're going to be talking about is the lateral side of the cylinder. That's horrible. Let's get rid of that one. Try again. The lateral surface here of the cylinder, the outside, and of course that's going to be around the outside. If I try and shade that in, it's not going to look right, but it's just the outside of the cylinder. So we are talking about a two-dimensional surface here that does have differences depending on where we are on the surface, and that's kind of what we're going to be talking about here. So what you could have is at some point right here, or at some point right there, or at some point maybe down here on the bottom, or at some point maybe on the top, you've got all these different little places on the surface, and every one of these pieces could have a slightly different density. So right there, down here, maybe up here, all of these could have a different density. Every single one of those points. And if you took little patches around those points, that's kind of the idea. If we took little patches that defined and made those little patches really, really tiny small, I mean really, really small. I don't know if I'm going to be able to draw this or not. We're going to give it a shot here. Like a really tiny little patch, close enough, around this thing on the outside of the surface, and then maybe one down here on the bottom of the surface, and so on. Take those little patches. If we add up all of those patches, so we'd be doing kind of a double integral. We'd be integrating a double integral, but we'd be doing it over the surface. What we'd be adding up is a whole bunch of little areas of the surface. So we'd be adding up the area of each one of those little blue patches, area of the surface, multiplied by each one of the densities there. And so what you really have is a two-dimensional area multiplied by this density, and then of course dA. That would be like the thickness of each one of these things, which would be infinitesimally small, which is why we call it dA. So really you do have a three-dimensional piece here because of that dA, and all of that is going to equal the mass. So what we're talking about there is having something where we're able to find the mass around the surface of a two-dimensional flat piece, because it's surface area, but in three-dimensional space. Hopefully I haven't lost too many of you guys yet. And then the other concept that we're going to talk about with this, I'm going to go ahead and draw one more cylinder here. Let's draw our cylinder. So we've got our cylinder here. The other concept is, now what if we have a vector field which is acting throughout this cylinder? So I've got different vectors doing different things all around this cylinder. The idea is that I've got some kind of a vector field, f of x, y, z, acting on this thing. So maybe this is some kind of, I mean, this could just be any region in space, but maybe this is actually one of those, I don't even know how else to describe it, like a laundry basket, like a foldable laundry basket things that has holes in the side or something like that, and I don't know how else to describe it. Some kind of a netting going around this thing where maybe fluid flows through it. So maybe you've got some kind of fluid flow vector field, or maybe it's some kind of wind going through some kind of a screened in, cylindrical shape or whatever. Anyway, but what you have is you have some kind of a vector field acting on this thing, and what we're going to end up with there is we're going to end up with the double integral of this vector field dotted with its normal vector ds. And what that's ultimately going to show us or give to us is this thing which we're going to come back to in later section, which is called flux. Basically the amount of stuff going in or out of some kind of a region. And that's kind of what we're looking at here, those two major concepts. in 16.6 to 16.9. So we're talking about how could we possibly find the mass around a surface and what we can do with the actual surface in three-dimensional space, and then what's going to happen as we have some kind of a vector field acting upon that surface.